Racist?
Yeah, it was very racist. Very racist stuff. That was not cool. Basically sharing a bunch of pornographic images on their computer and are on their feed and slinging the N-word around. So real classy shit that you would imagine frat boys would do.
What's up, everybody?
Hey, Professor.
Not much. What's up with you?
Nothing.
I'm trying to figure out a way to... Well, I don't know what I'm trying to do, honestly.
Well, that's usually the first task.
I am debating on whether or not to get a webcam.
Webcam? You don't have one?
I've got one on my laptop, just not on my actual rig.
When was your birthday, Denise?
It was during the COVID-19. I couldn't even go out and eat. Sucks. All I wanted to do was eat, and I couldn't even go out.
Why didn't you?
It was last month.
You could go get some.
Huh?
You can get takeout.
Yeah, Uber it.
Yeah, Doug, all the Mexican places are still doing it. Maybe you could ask them, hey, just let me wear the sombrero for a second. A lot of places are doing alcohol to go too right now.
Yep.
You can get a margarita and they just tape a little bottle of Jose Cuervo to the top of it. Boom.
Yeah.
Margarita.
Instant hand sanitizer.
Also, yes, but alcohol abuse, damn. I'm sober and that makes me sad.
All right, you guys ready to go?
Yes, sir.
How are determinants treating you?
Eh.
Talk to me about determinants.
Pretty
like
easy,
them,
really.
You hate them? Yeah, they're easy. They're just kind of tedious if you have to do them by hand.
Right.
Yeah. Yeah, they were tedious is a good way to describe a determinant.
I'm thinking about this okay, so we have, and I think this is what we kind of decided last time. We have a next homework due Thursday. Is that right? Today is the 7th. And we have a test due the following Tuesday. Does that sound about right?
Mm-hmm.
Yes.
Okay. Everybody cool with that?
Yes.
And the test is going to be over everything, including homework 7 that's due soon?
Yes. So it's through determinants.
Okay.
I think on the test, if I remember correctly, just because I think I had to, meaning, I wouldn't be able to sleep with myself if I didn't. I think that I asked you to do one 3x3 inverse with a letter in it, so you have to do that by hand, and one 3x3 determinant with a letter in it, so you have to do it by hand.
That's not so bad.
There are other determinants and inverses in there, and you are welcome to use your calculator, so some of those things will actually be like 10-second problems.
Hot dog. Sub Louis. Oh. 1 second.
All right. So I have those deadlines set like that, but I'll post something in NS Online kind of emphasizing when all that is. So post it.
I just got in here. Are we talking about the homework and test?
Yeah. So I think we just decided, like last week, homework 7 is due Thursday, and then the test through determinants will be due next Tuesday. Give you like a
Cool.
long weekend to work on it.
Yep, sounds good.
And that is also in NS Online, just like the homework you've been doing.
Yeah. And we've agreed that it's an, sorry, Close, I didn't mean to speak over you. Go ahead.
Nobody? Okay, so you all comfortable taking a determinant by hand if you had, and can you find one on your calculator?
Yes.
Doing it by hand's okay?
It's okay.
Okay.
I don't like it, but I can do it.
Yeah.
I'm okay with that. I mean, that kind of sums up life, you know.
Yeah.
So yeah, this formula that I taught you kind of involves, you know, it's what's called a recursive definition, where if I gave you like a 10 by 10 determinant, you would have every right to probably like hunt me down and kill me. But a 10 by 10 determinant, you would break it up into, you'd pick any row or column that you wanted to, okay?
Right.
And you would pick one with as many whats as possible.
Zeros.
Zeros, because that means you kind of, you get off the hook on determining one of those determinants of the, what's it called, the minor, I guess.
Right.
Mhm.
So you'd break that 10 by 10 matrix up into 10 determinants of 9 by 9 matrices. Okay. Each of those 9 by 9 matrices you would break up into 9 8 by 8 matrices, and you know, in 6 months you're done. Okay. So like I already told you, I think I give you a 3 by 3 on the test with a letter in it, so you kind of have to do it by hand. If I were to give you like a 4 by 4 or something, it would be a special matrix that, you know, you got to be able to think your way through. Like, for example, what types of matrices have easy determinants?
The triangular.
The triangular. Yep, either upper or lower triangular matrices. It's just the product of those diagonal entries. Okay. All right. So all I want to do today, and it might not take the whole time, but I know I say that a lot. So what I want to do today is finish up 3.3, which is like applications of determinants. And then we'll call it a day. And on Thursday, we'll start talking about eigenvalues and eigenvectors. So I think we'll be able to get through all of eigenvalues and eigenvectors. We have like 3 more weeks of school. Eigenvalues and eigenvectors, if you just kind of do the basics, which we're doing at this point, aren't too bad. And we might be able to get into what's called the dot product after that. So I'm hoping we have a couple days to talk about that. Nice and easy, but very useful.
Quick question.
Yo.
Or two, rather. So what we're doing today, Cramer's rule, that is the last content that will be on this quiz or test due Tuesday.
So besides Cramer's rule, there's also like the area of a parallelogram, which we'll also do today. But the stuff today is the last new material on the test. Yes.
Okay. And also, have you heard any word of them possibly extending this semester due to the?
I have not heard a thing about it. I was, you know, especially since they postponed graduation, I was kind of expecting to see something about like an extra week or something. Haven't heard a darn thing.
Okay. Roger that.
Okay. How are we doing? Clifford the big red dog?
Doing good.
All right, so let's talk about Cramer's rule. So this is named after Seinfeld's neighbor, who came up with this in the 90s. And it is yet one more way of solving square systems of linear equations. So by square, you have the same number of unknowns as equations. Okay. I know you're probably all thinking, gee, why do we need one more way? We got, you know, row reduction and inverses and all that stuff. And you are correct, but this is actually kind of a really slick way of writing down your solution. And in fact, I'll show you an example here where you have like a parameter floating through there doing row reduction, finding your inverse with a parameter is kind of a mess. And this thing kind of makes short work of it. Okay.
Nice.
Yep. So I actually asked you to watch one of those 3 blue, 1 brown videos on Cramer's rule, which is really cool. So I'm not going to duplicate what he did or derive it. I'm going to show you 2 examples and you'll be experts on it because it's very straightforward. It's just solving things requiring a bunch of, using a bunch of determinants. Okay. All right. So let me go over to my other screen here. And I've been getting fancy. I'm like, oh, what? You'll be impressed. Just a second. There, 2 things on one screen.
Oh, wow.
Yeah, I know. I hope you're all were sitting down. All right. I'm going to turn off my, you guys don't have to look at me, and I'm going to save my bandwidth for my rest of my family here. Stop video. I'm here if you need me. All right, so it says use Cramer's rule to compute the solution of the systems. Oh, heck, let's just grab number 1 over here. Okay. So I have somewhere over here. So we have 5. I'm going to use X's and Y's just because the subscripts get a little hard to do with this tablet that I'm on. And it's good for our brains. Okay. 2x plus 4y equals 1. Okay. All right. So the way this goes is we have 2 equations and 2 unknowns. So what we're going to do is we are going to kind of create 3 matrices. So it's always 1 more than the number of unknowns that you have. Again, it only works for square systems. So we're going to end up cranking out 3 matrices. So what we're going to do is the first one is going to be just a coefficient matrix. So over here, I'm going to say A is the good old coefficient matrix that we have on the left-hand side. 5, 7, 2, 4. Okay, clear what I did there? Now I'm going to create 2 others. One I'm going to call whatever you want. I'm trying to, well, let's call it A sub x because it kind of corresponds to my x variable, and I'll show you here in a second. Okay, so what I do, this is the time to wake up and listen. So what I'm doing is I'm taking that coefficient matrix, which nobody gave me a hard time about, so I think you're all okay with it. Okay, and what I'm going to do for this this one I'm calling A sub x is I'm going to replace the column that corresponds to the x that I have over here, the 5, 2. I'm going to replace it with kind of my right-hand side stuff, that 3, 1. So I'm going to go over here, and I'm going to have 3, 1, 7, 4. Okay. And then I'm going to do it again for my other unknown. So I have AY is going to be the matrix I get when I take that coefficient matrix, but I replace the Y column with the right-hand side. Okay. So before I do anything else, is it clear what I did? So if I had like a 3 by, yep, go ahead.
Shouldn't the AX and AY matrices be swapped, or am I stupid? Next to AX,
that's a false choice, neither one. So the X matrix is the one I get when I replace the X column with the right-hand side. So the 5, 2 up here,
okay,
that thing, that's like my X column. So that's the one that gets replaced for this guy.
Okay, I understand that.
Vice versa. Yeah, similar for Y. Okay.
Hmm.
So if I had like a 15 by 15 matrix, I could do this. I'd create 16 matrices. One would be my coefficient matrix. Okay. And then for each of my unknowns, I would get a new one by leaving out the column in that coefficient matrix corresponding to that unknown and replacing it with the right-hand side stuff.
Okay.
Okay. Now what I'm going to do is I'm going to crank out a bunch of determinants. And by bunch, I mean 3. So the coefficient matrix, okay. I'm just going to write the determinant equals 2 by 2s. We have a nice little formula, right? It's that cross product. So it's 20 minus 14, which is 6. We good?
Mm-hmm.
This guy, 12 minus 7, which is 5. I was going to say if I do something stupid, but when I do something stupid, let me know. And this determinant, I believe, is 5 minus 10, which is minus 5.
Mm.
Oh, sorry. No, did something stupid. That's 6. I was just giving you guys an opportunity. Okay. No, that's not right. It's 5 minus
Yeah.
6. I'll get it right here. 5 minus 6 minus 1. There we go. Okay. You still with me?
Mm-hmm.
Yeah.
All right. Now, what I'm going to do now here is I'm going to write my solution when I can find it. So my X answer, whoops, is going to be a fraction. It's going to be the determinant of that AX matrix in the numerator. In my denominator, it's the determinant of the A. Okay. So what I did was I kind of took this and put it there, and that goes all the way down underneath. Okay.
I can't see. I think it's a 6 from what you're saying, but I can't see that.
Yeah.
Really? I can see it. That's weird.
I've had issues with this thing since we started doing
It's
that.
okay.
It's just
So it is,
6,
yeah.
right?
So the denominator is that 6, which is determinant of my coefficient matrix. So it's
Okay.
my X unknown ends up being 5 over 6. Okay. What do you think my Y unknown is equal to?
1 over 6.
1, but with the minus sign. Okay.
Negative 1
So
over
my
6.
AY is minus 1, and I divide by 6. So that guy goes right there. And that 6 also goes there. So the determinant of my coefficient matrix ends up being my denominator for all these things. And the numerators end up being the determinants of those, I don't want kind of extra matrices I get when I do that little column replacement. Okay. So quickly I'm plugging into my head. So 5 times 5, 6 is 25, 6 minus 7 is 18, 6, which is 3. 10 minus 1 is 6, 6, which is 1. Check a root. Okay.
What did we just do?
I just checked it in my head.
Okay.
So this just kind of gives us the scalars of the X and the Y, the X and the Y vectors within this matrix or system of equations that gives us the specific 3, 1 vector.
Gives us the specific. Oh, yes, exactly. Yep. So if you watch that video that I sent you, you should. It's good. It's a really good one. Like I said, when I first saw this, I went through a mind-numbingly boring proof. I thought, yeah, okay, it works. But I didn't really understand what was going on until he put out this video a few months ago, and then it all clicked. I thought, oh, I see what's going on.
I haven't watched it yet. Is that in the week 2
Yep.
thingy?
Yes.
PDF? Okay.
Yep.
I will watch.
I think it's also posted in learning resources on the Discord.
Okay.
What's kind of going on here is that, you know, we want to find out what, if we think of this as a linear transformation, we're trying to figure out what we have to plug into to get to that 3, 1 vector on the right-hand side. So in some sense, there's kind of like an inverse going on, right? I mean, if we were to crank out this inverse, we would just say, hey, take that 3, 1, multiply it by the inverse, and we get this thing. But what's going on with the determinants? So if you look at that A matrix, okay, that corresponds to the coefficients, its determinant is 6. So that basically is telling me that I'm kind of stretching everything in that direction by a factor of 6. So when I go backwards, I'm going to have to be, in some sense, dividing things by 6 to kind of make it work, right? And that's how this dividing by 6 shows up. Okay, so I get a 6 in my fraction because it's kind of bringing me backwards. Some of you, when I actually asked you to crank out an inverse by hand, some of you, bless your hearts, because I'm all for it, is you went out and learned how to do it using something called an adjugate matrix. Okay, I was kind of expecting people to just do the RREF, where you augment with the identity and then see what comes out. Okay.
Yeah.
The adjugate, for those of you who went that route, it also involves it dividing by your determinant. So that's what's happening. Is kind of the determinant tells you how much you're kind of stretching going forward. And so these inverses all kind of end up with a determinant in your denominator when you go backwards. Okay, so I'm going to do another example or two, but is it kind of in this one example, is it clear what I did? So I have two unknowns, so I created three matrices. One with my coefficients, and then I kind of swapped out my right-hand side for various columns as I went, and then I just looked at ratios of determinants.
I'm clear on the mechanics. What I'm not so clear on is the application of these fraction values.
I'll show you here in a second.
Okay.
Okay, so far so good?
Yeah.
Okay. So the application, or the reason I kind of like this, what I like Cramer's rule best for, is look down here like number 7 in the bottom left. So the way they phrase it is they say determine the values of the parameter S. So they have this S floating around our system of equations. Okay. Determine the values for which the system has a unique solution and describe the solution. Okay.
Oh.
So what I'm going to do is I'm actually just going to drag my S through Cramer's rule, and I'm going to end up with a nice expression giving me my solutions in terms of S. Okay. One other thing that's going to come out of this, I don't know if I actually said this before, if it just kind of, it got pretty far up in my brain. I don't know if it came out my mouth. So in this Cramer's rule method that I just did this example on, what's the one thing that could really go south on this?
You have a determinant of 0?
Exactly. Okay. In this case, I was dividing by 6, which is perfectly cool. But if I want to divide by 0, not so cool, right? Okay. So if the determinant of your coefficient matrix is 0, Cramer's rule just stops. Okay. Because what is going on, and this is all tied together, this will sound familiar. If the determinant of your coefficient matrix is 0, that means that matrix is not invertible. So that means you're going to have not a pivot column in every column, and that means you're going to have a free variable. So if the determinant of that coefficient matrix is 0, you can't use Cramer's rule. But that also tells you that you're in the situation where either you can't solve your equations at all, or you have many solutions. Okay. So that's what's going to come out of this when we do number 7 here in a second. They say determine the values of the parameter S for which the system has a unique solution. That's just going to be the values of S that make that coefficient matrix have a non-zero determinant. Okay. And they say describe the solution. That's just going to be Cramer's rule. All right. So let me clear this and kind of write that down. Okay. So this is number 7 here. Okay. So I have 6S, where S is anything I want, X plus 4Y equals 5. And I have 9X plus 2S equals minus 2. Okay. Oh, hang on here. I forgot my Y. Sorry, I thought I was, all of a sudden I decided to move to the matrix form right away. Hang on. Ah, there we go. Ah, yeah. With you in a second. Okay, so I had number 7. All right, so I had 6S x1 plus 4x2, and now I guess I'm using the x1s and x2s. I only have coffee here. It might go better if I went and got a beer. So I have 6SX, and I was going with X's and Y's. Okay. This was 9X plus 2SY equals minus 2. Okay. So this parameter S actually shows up as part of my coefficients. Okay. And therein kind of lies the rub. So when I go to crank out these 3 matrices, my first one, It's just going to be my matrix of coefficients, but I have this S floating around here. So in that first row, my first coefficient is actually 6S. My second one is 4. Okay. Second row, I have a 9 on my X, and I have a 2S on my Y. Okay, so I have to drag that S along for the ride. Next thing I'm going to do is I'm going to crank out the matrix I get when I replace the X column, which in this case is 6S and 9, with the 5 minus 2. So 5 minus 2, 4, 2S. Okay. And lastly, I get AY. I replace my coefficient matrix. I replace the Y column by that 5 minus 2. First column stays the same. So far, so good?
Yes.
Okay.
Yes.
Now what I'm going to do is I'm going to crank out a bunch of determinants. Notice in each one of these, I still have an S floating around. Okay, but I'm still just using that 2 by 2 determinant formula. So here I get 6S times 2S is 12S squared
36.
minus 36. Down here, I have 10S plus 8, I believe. 5 times 2S is 10S minus 8. So 10S plus 8.
Mhm.
And down here, I have minus 12S minus 45.
Yes.
Okay. So my X answer is going to be this AX. So remember, the coefficient determinant is my denominator. So my X answer is going to be 10S plus 8 over 12S squared minus 36. And my Y answer is going to be minus 12S minus 45 over that same 12S squared minus 36, provided what does not happen?
S
12s
doesn't
squared minus
equal
36.
You got it. So down here, I would try to sneak in and say, provided (12) S squared minus 36 is not equal to 0. Okay. And I believe that means, so if I add 36 divided by 12, I get 3. So I think that is telling me S is not equal to plus or minus square root of 3. Okay. So if S is the plus or negative of the square root of 3, then this thing breaks down and doesn't work at all. That's the situation where either I can't solve it at all or I can solve it with an infinite number of solutions. Okay. If S is not equal to plus or minus root 3, then these two expressions right here tell me exactly what my solutions are. I just plug S in and knock them out. Okay. So to answer this question, the values of the parameter S for which the system has a unique solution, well, I want that determinant of my A to be non-zero. So in this case, S is not equal to plus or minus root 3. And describe the solution, that's the expressions I got there in X and Y. So in particular, if S happened to be 0, okay, this is telling me that X would be 8 over minus 36 or minus 4/9 or something like that. Okay. So one of the things I like to ask on a test, but I don't think I can fit it on yours because it would probably take me 2 hours to write it up, is for what values of S is the answer X actually equal to 0? So what would you do to find out what values of S give me a 0x? I would take that expression for x, set it equal to 0. Okay. A fraction is 0 only when the numerator is, so I would solve 10s plus 8 equal to 0 and get s equals minus 8/10 or minus 4/5. But for the test you're going to be taking, or the homework, I think what I just wrote there would be sufficient. And nicely done. Questions? So again, the advantage to using Cramer's rule for this is you could do it using like row reduction, but dragging that S through it would just be kind of a mess. And I think you all agree that cranking out 3 relatively straightforward determinants and then writing 2 ratios wasn't too bad.
Yeah, no, it's not so bad.
Yeah.
So the alternative would be just to take the augmented matrix of that original set of
You got it,
functions
and start your row reduction. Yep. And so you have to drag that S through everything.
Oof.
You know, you'd want to get a 1 on the top left, so you have to divide the whole top row by 6s, and you know, it's doable.
Yeah,
you know, take many years and cost thousands of lives.
I think I like this better.
Yeah, me too. Again, it only works when you have a square system and when that determinant of the coefficient matrix ends up not being 0. Questions, comments? We doing all right?
Straightforward. Yeah.
It's pretty straightforward.
It is. Again, 3 or 4 or 5 or whatever, not harder, just more tedious. You just have to do more of them. I guess your determinants are worse. So, you know, again, I could envision myself asking you guys to do like a 3x3 system this way, but even then I would want the determinants to come out not too bad.
Cool. Much appreciated.
You're welcome.
Yeah.
Okay, what else we have to learn today?
Area of a parallelogram.
Area, yeah.
Yeah, so I want to talk about areas. And I'm just going to grab an example here. I want to do something first before I jump into like one of these 19, 20, and so on. Okay. All right, so here's a cool thing about determinants. So let's say I got 2 vectors in R2. What might that be, 2, 5? I'm just making this up as I go. Okay. I got 2 vectors like that. One of the things you're just dying to do at this point is just to make a matrix out of them, right? So if I do this, I got some obvious matrix, correct? So what I want to talk about, and by talk about, I mean, I'm just going to teach you how to do this because it's really easy, okay, is what does the determinant of that matrix have to do with those 2 vectors? Okay. And it turns out that what it gives you is it gives you the area of the parallelogram that those 2 vectors determine. Okay. So this area in here is your determinant. Okay. So in this case, the determinant of this guy is what? 15 minus 4, which I believe is 11.
Ah.
Easy peasy. What if I had picked a kind of a degenerate case where I had picked 2 vectors that were linear multiples of one another? So let's say I'd done something like this. Let's say I had picked a 3, 2, And then I just got wild and wacky, and I picked a 6-4. Okay. What type of parallelogram do those two things determine?
Straight line.
Yeah, it ain't much of a parallelogram, right? So what happens when you crank out the determinant?
It's literally just the length of the line.
0,
Careful.
0.
Yes.
Because if 3, 2, and 6, 4 are multiples of one another, these columns are not linearly independent, and that tells me my matrix must not be invertible, and so my determinant has to be 0.
That makes sense.
We doing okay?
Yep.
So, in fact, let me put down in here, no real and I'm going to leave it like that because I don't want to spell parallelogram. Okay. All right. The same thing happens in more dimensions. Let's see here. In fact, look over here on the left at number 23. It says find the value. So I don't know who came up with this name, but in more dimensions, they call it a parallelepiped. Okay. I usually call it a box. It's a lot shorter to write. So they say find the volume of the parallelepiped with one vertex at the origin. And I'll show you, I'll do an example here in a second where we don't have to have that be the case. We kind of translate everything to the origin. Find the volume of the parallelepiped with one vertex at the origin and adjacent vertices, and they give us 3 vectors. All we do for this, number 23. All you do is you crank out the determinant. In this case, it's a 3 by 3 because I'm living in R3. 1, 0, minus 3. 1, 2, 4. 5, 1, 0. That's all you got to do, and that will give you the answer to 23. Okay. If it ends up being 0, that means they kind of messed with you a little bit. That means they gave you 3 vectors that are not linearly independent, and they don't actually determine a box. They kind of determine a plane. Okay. But in this case, I would probably just get out my calculator. But this isn't too hard to do by hand. So I'm going to expand down the first column. So I get 1 times the determinant of what? So I leave out the first row in the first column, and I get 0 minus 4. Okay. I have minus 0 times something, and then I have plus minus 3. And what ends up, what do I get when I leave out the row in the column that the minus 3 is in? I believe I get 1 minus 10 is minus 9. Okay. Which is minus 4 plus 27, which I think is 23. That's your answer.
What is that after?
Oh, they did something cool there. The answer number 23 is 23. Wow. I hope they didn't stay up all night doing that.
Yeah.
Okay. Now, what if that had been minus 23? What would you do instead?
No, you just take the absolute value.
Yes, you do. If there's a minus sign there, you just forget about it. Okay. Remember last week I was telling you that when you have a minus sign, that's telling you that there's some orientation kind of going on there. Okay. We don't care about the orientation as far as volumes and areas go.
I have a question.
Go for it.
You solving the determinant, I'm confused on how you got the numbers like 1, -4, 0, and whatnot.
Okay, so I expanded down my first column. Okay. So for this thing, I'm going to go down here. So remember my pattern for 3 by 3s. I have to keep my hand off that little button. What did I do last time? Oh, I had to like, okay, hang on. I have the fix for this. I have to
On your
unplug my
house,
tablet,
not that
plug it
dark.
back in. Justice, how are you?
I'm good.
So how we, uh-oh, this is proven problematic.
Abstract art.
Yeah, I didn't mean it to be.
Mhm.
I thought last week I just unplugged it and plugged it back in. No, I don't mean to be doing that. Oh, I wonder if I can do this. No.
This is mildly amusing.
Yeah, not for me. Oh, cool ruler. I swear I don't have the selection thing done. Oh, I wonder if, okay, I can get around this. Okay, I'm going to annotate on top of this. So no. Nah. All right, starting to lose my stuff here. And by stuff, I mean my. Oh, this will work. Okay, so I had minus, I had plus, minus, plus, minus, minus, plus. Okay. So if I'm going down the first column, first I'm going to use 1 times, and what I'm going to do is I'm going to leave the row and the column out that 1 is in. And what smaller matrix am I looking at? When I leave out the first row and the first column, I'm looking at that 2140 right there.
Yeah.
I'm going to kind of square it, and then I'll undo it here in a second. Okay. So it's 1 times the determinant of that thing. And the 2 by 2, which you should memorize, is it's top left times top bottom, which is 0, minus the other 2. So in this case, it's 0 minus 4 gives me the minus 4. Then as I'm going down, I'm going to have a sign change. So that's why I have minus 0 times. And since it's 0 times something, what it would be is I would leave out the row and the column that 0 there are in. Okay. So I'll be looking at a determinant of 1540, but I don't care because I'm about to multiply it by 0. So then back to another positive. So I'm going to keep whatever sign is about to come. I'm down to the minus 3.
Okay.
And the minus 3 times. So I leave out the row and the column that the minus 3 are on.
Mhm.
And what is left is that matrix right there. And my determinant there is 1 times 1 is 1, minus 2 times 5 is 10. So 1 minus 10 gives me that minus 9. Okay. So now I do 1 times that minus 4 is minus 4, nothing. And then minus 3 times minus 9 is plus 27. And I add them up and get my 23. Okay.
Okay, I got you. Makes
Okay.
sense now.
Yep. Let's see. I think time-wise we're doing okay. Let me check. Oh, you were doing good. Let's see. I want to do one more of these. Take a look at 21 over here on the left-hand side. Okay. So 21, they don't give us 2 vectors in R2, or they don't come right out and give us 2 vectors in R2. But I claim there are kind of 2 vectors that I'm going to take and put into my matrix here in a minute once I kind of figure out what my vectors are. So if you got a pencil and a piece of paper, and you should, just do a rough sketch of where those 4 points are in R2. That shouldn't have to be too fancy here. And let me see if I can figure out what I'm doing here. And I know the short answer to that is no. Clear all drawings. Okay, so let me see if I can do a halfway decent job of that. I want to get that out of my way. Well, I guess it ain't going anywhere. Okay, so what do I get? So I got -2, 0. Roughly over there. 0, 3. 1, 3. And 2, 1. So something like that. Okay, 0 minus 2. Wait, am I looking at the wrong thing? No.
Minus
Yeah, nope.
It's minus 1,
I
0.
combined problems again. Yep. So -2, 0, -1, 0. I got those things right there. Those 4 points?
Yep.
Ooh, that looks, oh, the parallelogram I'm about to draw is much better than what I would have drawn about 20 seconds ago. So my parallelogram looks to be kind of that right there. Okay. So if I want to figure out two vectors that kind of determine that parallelogram, I have a little bit of leeway here, but I think what I'm going to do, not that it matters, I'm going to kind of pick that to me by base point. And let's figure out what that vector is and what that vector is. Okay, so I'm kind of, I guess in fancy terminology, I'm kind of translating this thing to the origin, but I want to figure what those outcoming vectors are from that base point that determine that parallelogram. So what is the vector that goes from this guy to that guy? So it's going from -2, 0 to 0, 3. So this vector right here must go 2 to the right and 3 up. You see what I did there? I'd subtracted in my head. That vector must go 2 to the right and 3 up. That guy right there. Okay. How about this this bottom vector here going left to right? So that's going from -2, 0 to -1, 0. So that vector right there must be, what is its direction? So I can just kind of tell by looking that I'm going 1 to the right and none up. But if I don't, trust myself just by looking, I could subtract. I'm taking that -1, 0, and I'm subtracting the -2, 0. Could be my chair too. Okay. That is the hard part. Are you all okay with what I did?
Yep.
Okay. Now what am I going to do? I'm just going to crank out a determinant of 2, 3, 1, 0, which is 2. I guess if you want to use just base times height on a parallelogram, you don't really need to get fancy with the determinant, but gosh darn it, we know what determinants are, so we're going to use them. Okay. So the only difference over there on the left between 19 and 21 is that in 19, well, actually, I guess I haven't done 19 yet, or did I? No, I have not. Okay. But 19, one of our base points is the origin, which might make this just a little bit easier, okay? So you kind of plot your points and you figure out which two vectors are kind of the two sides of your parallelogram. Then you just plug them into a matrix and take your determinant.
And that's the entire area?
That's the entire area of that parallelogram.
Okay.
Not 3 or -3 or whatever?
Did I screw something up? Heck yeah, I did. Wait a minute, base times height. Yeah, it's got to be. No, really, I can do this. Okay, so what is that? 2 times 0. I no longer trust myself at all. 2 times 0 minus 3 times 1, which is minus 3. Thank you. Okay. Base times height. Yeah, so it's a height is 3. So my area, remember, what do I do here to get my area?
So leave off the negative, right?
You got it.
No negative.
So we're going from, is the base arbitrary?
Oh, what do you mean by
Can we do it
arbitrary?
start-
The
can we
point that I
start at
kind of
any-
picked as my starting point?
Yeah.
Yeah, that's, you can kind of pick whatever you want. That's going to kind of change what your 2 vectors are. Like if I had chosen the top right, if I had chosen, let's see how fancy I can get. If I had chosen this to be my base point, then that vector there would have been minus 1, 0.
Yeah, yeah.
And that
minus-
vector there would have been, what is that? Minus 2, minus 3, I think.
Yeah.
Backwards.
And why don't we need the 4th vector? Because isn't that a part of determining what this parallelogram looks like?
Because once I know 2 sides of that parallelogram, as long as I don't pick 2 parallel sides, I know everything I need to know about that parallelogram. Because I know that
Okay,
the other
cool.
2 vectors out there must be the same length and the same orientation as the 2 that I picked.
Okay.
So that's kind of superfluous. Okay. So if I were to kind of do this one, so it looks a little different. But I get out, double check me on that, 3 minus 0, which is 3. Okay. So absolute value wise, I get out the same thing. Okay. Again, all that's changing with that negative, and I don't want you to worry too much about it, is the first choice I had there, I wrote the 2, 3 first. So I'm kind of doing 2, 3, and then the 1, 0. So as I kind of walk around in that order, I have that area to my right, which in mathematics is kind of backwards. So it ends up being a minus 3 orientation. I drop the minus sign anyway. From this perspective, if I did the minus 1, 0 first, and then the minus 2, minus 3, I'm actually walking around that region with that area to my left, which is a positive orientation. Do not worry about that. If you see a minus sign for an area, you just drop it.
So this is just giving us the area of the
Yes.
subspace within the dimension that we're working.
You got it.
Alternatively, we can also just have a 2x4 matrix, 2x4 matrix, no?
What would you do with your 2x4 matrix?
Oh, we can't find a determinant of that, can we?
Exactly. Yep.
Gotcha.
Ah,
Tricky.
Yep. So you do kind of have to do, I did some subtraction here in my head to figure out what those vectors are. Okay. But once you draw your picture, you should kind of see, okay, those are my 2 parallel sides and those are my other 2 parallel sides. Okay. Those parallel sides, those pairs, they're always the same vector. Okay. It kind of has a different base points when I think of them as sides of my parallelogram, but they're the same vector, each of those opposite pairs.
And this will only work for 4 points then. Anything higher than that?
In R2, yes.
Yeah.
Okay. So in R3, do they actually give you any over there? No, it's just kind of too mind-numbingly there to actually do it. So if like 23, I already did that. Say find the volume of the parallel pipe bed with 1 vertex at the origin. So in 24, they do that as well. So they kind of give you a base point, and then those 3 points that you have, they're your vectors.
Okay.
So 0 is a nice base point as far as vectors are concerned.
Cool.
Okay. Take a look at 25 because I like this kind of stuff. It says, use the concept of volume to explain why the determinant of a 3x3 matrix is 0 if and only if A is not invertible. I kind of mentioned this before. So if I have a 3x3 matrix and I think about the columns as my vectors that kind of determine that box or that parallelepiped,
Yeah.
I'm going to have some decent box as long as my 3 column vectors do not what? do not end up being linearly dependent. So if any one of them is already in the plane determined by the other two, in other words, they're dependent, I'm going to get a degenerate box. I'm going to get something that's like a flattened box with no volume.
Okay. Neat.
All right, how are we doing on areas and volumes?
Good.
Good.
Because the last thing I want to talk about is actually how a linear transformation changes these things. Okay. And I mentioned this the other day, but a linear transformation is just kind of stretching things by a factor that's equal to the determinant of the associated matrix. But we'll do something here in a second. Okay, let me clear this thing. If I can find it. Okay. That'll work. Okay. So if I have a pen, okay. So let's say I have a linear transformation that's grabbing some region, okay. So let's call this area, let's see, because it's too bad that A stands for area, but it's also my kind of my matrix. Oh, let's call it V for volume. It's a two-dimensional volume. We'll call that volume, okay. And over here, that linear transformation takes that region, and the region it spits out is some other region, okay. So we shall call that T of V, okay. So the relationship is this. So if A is the matrix associated with T, and again, all these linear transformations are associated with matrices. So if A is, let's get fancy and call it the standard matrix of T, then the volume of the output region is equal to the volume of the region that you kind of plug into it times the determinant of that matrix. Okay. I'm going to rewrite that because I'm not at all happy with that right-hand side. Oh, I wonder if I could do.
If A is the standard matrix of I, what is?
Sorry, I meant to write T. Thank you. T. Then that's the determinant of A times the volume of V. Okay. So for example, well, yeah, I can probably sneak this in. Okay. So let's say we have some matrix, and I'm just going to make one up. 3, 1, 2, 4 will work. Okay.
One more question, sorry.
No,
At the end
no problem.
Of the last line, is that volume of V or T? Because it looks
Volume
like a
of
combination
V. Sorry, that's a V. I don't want to do that. Okay. It's getting worse instead of better. Okay. So basically what is going on here is that a linear transformation with a matrix is stretching volumes by the determinant of that matrix. Okay. So for example, this one here, I didn't even go to the linear transformation, I just told you the associated matrix. So the determinant of A is 12 minus 6 is 6. Did I do that right?
Yep.
Yeah.
So if I have any region over here, in particular, what happens if I look at what's sometimes called the unit disk? Okay. So if I go 1 in the positive X and Y direction, I have a region of area 1 in here. Okay. My linear transformation is going to spit out, let's see, 3, 1, 6, 4. It's actually going to end up spitting out something that kind of looks like that. But even without knowing the particulars, I know that if I feed this thing a region of 1 and let my linear transformation operate on it, what is the area of what comes out? It's 6 times whatever area I just plugged in. And if I just plugged in a region of area 1, that's just 6 times 1. So if I were to plug in something with an area of 50, the output of that thing simply gets stretched by a factor of 6, and out comes a region of size 300. If the determinant had been -6, I just forget about the minus sign. That tells me that it's kind of flipping around in orientation, but as far as the areas go, it doesn't care about orientation. Okay. So for example, let's take a look at number 27 over there on the left. It says, let S be the parallelogram determined by the vectors. They give us 2 vectors, okay? And let A be some matrix. Compute the area of the image of S under the mapping, so what we would kind of call our linear transformation T, that takes a vector X in R2 and multiplies it by that A. So where was I, 27? So we will make pretty short work of this one. So I have -2, 3, kind of like that. And I have -2, 5, kind of like that. Okay. And I just put myself in a box where I can't, oh, let me see if I can do this. Oh, it ain't gonna stretch it that far. Oh, that'd have been nice. Nope. Oh, ooh, ooh. It's the little things in life. Okay, so this region over here, I said this region over here has what size? So I got some terrible parallelogram in there. I don't care too much about it geometrically because all I'm going to do here is I'm going to figure out the area. So what's the area of that thing?
4.
I have no idea. You're way ahead of me. But what do? Is I make those 2 vectors into a matrix. So -2, 3, -2, 5. And I get out -10 plus 6, which is -4. Yep. Okay. And I suppose I should say it's the absolute value of that because now I need to drop a minus sign. Okay. So one key to this whole thing is that that parallelogram determined by those 2 vectors has an area of 4. The other thing I need to know is that matrix of that linear transformation has what determinant. So I crank out another determinant and I get out 12 minus, am I doing this right? 12 minus 9 is 3. Did I do that right?
Yeah.
Okay. So what this thing is telling me is that I'm feeding it an area of 4. That linear transformation is stretching everything by a factor of 3. So what's the area of the output? It's just 3 times 4.
Cool.
Which is 12.